We're going to look today at development boards, experimental boards, all the different types and why we should use them. We are well catered for in Merg, in that there are a great many kits to choose from. You order the kits, it comes with all the parts identified and full assembly instructions. If you follow the steps, you should end up with a working module. But what if you want to go beyond that and you want to experiment, try alterations, etc.? What are your options? You may, for example, see a circuit on the internet, like the one shown here, and you want to check it out. You want to build it, see if it works. You want to experiment, see what happens if you alter the value of, say, R1 or R2 or C1 or whatever, and learn along the way. You may want to extend the functionality of existing circuits or kits. The laser detector kit, for example, it's an excellent kit, and it's got a digital output, and that's handy for switching LEDs or interfacing to EasyBus or C-Bus systems. However, you may want to add a relay or some other device, and there is no spare space on the PCB. So how would you alter the circuit? Or at a later stage, once you get more experience, you may want to have a go at developing your own circuits. In all these situations, you need some foundation on which to build. So you start with the idea. You're going to make up a temporary build to see if it works, experiment with it, and hopefully finally ending up with a fully working module. Other considerations may be whether you want to build a permanent module, or you just want to test something out or try to work out how something works as a temporary feature, or whether you intend it to be a permanent module sitting on your layout. And then do you want to make just one of them, or do you need lots once you got it working? In which case, you may be considering a PCB version once it's fully tested. Well, here we have the simplest approach to soldering, where we're soldering in mid-air, which is fine for a quick lash up just to test something using bits of wire and so on, for a very temporary arrangement. Of course, it doesn't work when you get to more complex circuitry, and there are better ways. A very common method is the use of breadboards. They consist of a plastic case with multiple holes. Inside the case, there are rows of sprung metal contacts. When you insert the lead of a component into one of the holes, it makes contact with one of the metal contacts, and also any other components inserted in the same row. Many breadboards also have columns of contacts down the sides, and they are mostly used as a means of distributing power to devices and components along the board. You simply push the wire leads of the components or the legs of chips into the holes, and you use additional wire links as shown to connect rows where necessary. And here I am testing the best values for a circuit that would later become a merge kit. And this is the test set up for an Arduino Nano reading a temperature sensor and then sending the results via a radio transmitter module. And this is the start of the build of the receiving module. The radio receiver is over on the left, and it will feed its output into another Nano. And that Nano, in turn, will use the data to display the temperature on the OLED screen. Note that in this case, the long outer rows are split in two. This allows, for example, to have 5 volt modules fed from one end and 3.3 volts modules from the other. In this case, however, I have connected the two sections together with bridging links. These examples show wire links using solid core wire, but more commonly, links are made using on dedicated jumper wires, and these have prods at each end. You can also buy power supplies that fit on the outer power strips, and jumpers are used to set the supply voltage to 3.3 volts or to 5 volts, or even 3.3 volts down one side and 5 volts down the other side. Breadboards have a number of advantages. They're quick and easy to set up, especially with simple circuits. With simple circuits, you can even make the breadboard component layout look similar to the schematic layout, so it's easy to understand what components are doing. Another advantage is the components can be easily moved around. You simply unplug a component lead from one place and insert it into another place. That way, any mistakes you make, any alterations or additions you want, are quickly tackled. If necessary, you can even link several breadboards together, either to build a larger circuit or to connect two separate projects you've been working on. And lastly, the components that you use are all reusable. They've not been soldered, they haven't been cut and trimmed, so you simply have to unplug them from the breadboard and you can use them again and again. On the other hand, breadboards are not without their problems. The larger the project on a breadboard, the more confusing the layout becomes. Jumper leads creating a spaghetti junction, and you lose track of what components are for and why that link is there in the first place. And most important is that poor contacts can sometimes happen. Breadboards rely on a good, consistent contact between the component leads, jumper leads and so on, and the breadboard's contacts. If for any reason they become loose or high resistance, then the contacts suffer and can lead to wasted hours locating faults that need not exist and were not caused by circuit design errors or wrong components. And the best way to achieve reliable electrical contact is, of course, by soldering. And there are a number of options open to us here. We can solder components and their leads to each other. We can solder components leads to copper pads, or we can solder them to copper tracks. Now, when I'm talking about soldering components to each other, I don't mean this. I'm talking about mounting them in a board that can secure their position and provide a permanent module if required. And here's an example, sometimes called bare perf board or punch board or vector board. Bare because they've got no copper on them whatsoever. It's simply a flat piece of insulating material with a grid of holes drilled through them. Here's the Farnell product, which I describe as made of epoxy glass composite, while the Rapid product here is described simply as hard paper. And here are some examples of boards made up by Chick. You'll see the components mounted on top generally, and the wiring underneath or sometimes above the board. Another one controlling a stepper motor, and a selection of semi-permanent modules. It has the advantage that you can control component placement and achieve a quite compact layout as a result. It's also possible to buy a tool that inserts a kind of standoff on the top side of the board, as in this example. If we go that far, you might think, well, why not have copper pads instead of expensive standoffs? And that leads to these boards. They're like the previous boards, except that they have a copper ring around each hole. They can have slightly different descriptions, but they all have the same distinct copper grid pattern. And they're available in a range of sizes and shapes. Some have additional pads round the edges, and some have pads that are designed to plug into a PCB edge connector such as this, for the building of even more complex projects. Here's an example of one in use. It's the module I made up to control the dot matrix display. And you'll see that since the component leads are soldered directly to the board, they're held more securely in place. Now, the most common spacing on these boards is 2.55 mil between the centre of each hole, or 1/10 of an inch. That's pretty much the standard up till now. However, with the trend towards more and more miniaturisation, boards with smaller spacings are available. This may make adding surface mount components more easy, or allow connections such as those tiny 1.27 mil pitch JST connectors. Okay, enough about copper rings. What about boards with copper tracks? Now we're coming to our good old friend, the Euro board, or strip board to give it its generic name. Initially, all the pocket money kits in the range used strip board, and many still do. Once again, we've got a piece of insulated board with pre-drilled holes on them. In this case though, the underside has multiple tracks of copper laid on it. The components are still inserted from the top side and soldered to tracks on the underside. So, soldering a component lead to any point in the track makes contact with any other component that is soldered to the same track. Once again, we can create a semi-permanent or permanent module this way, converting something like this to look something more like this. When you start to work with larger circuits, you'll find that the number of tracks there will be a limitation. And again, you can get round that by cutting the track to create extra segments. A few twists of this particular cutter here, and the track is split into two electrically. In fact, some versions like the one shown here has already got a split up the middle, and this allows the easy connection of ICs, etc., because they can straddle the gap. Even better for bigger projects is the availability of larger strip boards that are already segmented. Again, these boards come in a range of formats like this one, or this one, or this one. You'll notice that they often have a combination of segments and individual pads. That way you get the maximum flexibility in your build. And some also have unbroken copper buses running down the board. These are often used for distributing power throughout the board. Here's a blown up version of one of the boards that I showed you earlier. You can quite clearly see that it's got 4 sets of buses running vertically. Other boards, like the one mentioned earlier, have got pads for plugging the board into edge connectors. I use these boards for help in programming PIC chips. The image you see there shows both my 8-pin and my 14-pin boards. Each board has got a ZIF socket, and that allows the safe and easy insertion and removal of the PIC chips without any damage to their legs. And you'll see the cables heading off to the right, heading towards the PIC programmer. The boards also though double up as a mini development board, as I've got all the pins taken out to the sides and labelled, as you can see. And at the bottom I've got some LEDs, switches, push buttons and so on to allow me to carry out some basic tests. And if you're into serious development and experimentation, how about this board? As you can see, it combines segmented sections and individual pads, and areas for including surface mount components as well as the usual through-hole components, and also provision for mounting various sockets. Finally, let's look at some dedicated and adapter boards. For example, this one can accommodate anything from the usual 8-pin PICs and ICs up to 20-pin chips, with each pin taken out the pads for the easy connection of components. So if you want to quickly rustle up a circuit based on a PIC or an integrated circuit, you might find this one handy. Along similar lines, here is a board for handling surface mount chips. Right, let's wrap up by looking at surface mount development and these little converter boards. Here's a tiny board for soldering on an 8-pin surface mount chip. Each pin connects to one of the outer pads, and these are spaced 2.5mm apart. So just solder on a couple of 2.5mm pin headers, and the surface mount chip can now be attached to any development board using the common 2.5mm pitch holes. You've just converted a surface mount chip into a through-hole component. And you're not limited to 8-pin devices. A whole range of adapters is available to you. In conclusion, as you can see, there are many options open to you. Whether you're making basic tests or developing a whole new project, there's a board out there for you.